Anything that moves through the air reacts to aerodynamics. It is the study of forces and the resulting motion of objects as they fly through the air. When a baseball is thrown or hit, the resulting motion of the ball is determined by Newton's laws of motion. From Newton's first law, we know that the moving ball will stay in motion in a straight line unless acted upon by external forces. We see that there are external forces because baseballs do not move in this straight line forever.
Curve the soccer ball in midair. It's one of the coolest things. And
look at the banana he gives this one. Work on it to bring it back in. Look at this laser shot we have.
There are three forces that act on the flight of a baseball. The forces are weight, drag, and lift. Lift and drag are actually two components of a single aerodynamic force acting on the ball. Drag acts in the opposite direction to the motion, and lift acts perpendicular to the motion. Let's consider each of these forces separately. First, we'll look at weight. Weight is the force that is always directed towards the center of the earth. In general, the magnitude of the weight depends on the mass of the object as determined by Newton's law of gravitation. By rule, the weight of a Major League Baseball is 5 ounces. We can often think of weight as a collected and acting through a single point called the center of gravity. In flight, the ball rotates about the center of gravity. Newton's laws of motion describe the translation of the center of gravity. The physics describing the rotation, translation, weight, and center of gravity of a baseball is the same for any ball. Drag. As the ball moves through the air resists the motion of the ball, and the resistance force is called drag. Drag is directed along and opposed to the flight direction. In general, there are many factors that affect the magnitude of the drag force, including the shape and size of the object, the square of the velocity of the object, and the conditions of the air, particularly the density and viscosity of the air. Determining the magnitude of the drag force is difficult because it depends on the details of how the flow interacts with the surface of the object. For a baseball, this is particularly difficult because the stitches used to hold the ball together are not uniformly or symmetrically distributed around the ball. Depending on the orientation of the ball flight, the drag changes as the flow is distributed by the stitches. Let's look at this a little bit closer. If we move with an object through the air, the object appears to stand still and the air moves past the object at the speed of the object. Next to the surface of the object, the molecules of the air stick to the surface. This is called the boundary layer. This thin layer of molecules pulls on the surrounding flow of air. Unfortunately, the state of the boundary layer is not the only factor that determines the drag of the object. Size, shape, and atmospheric conditions also affect the value of the drag. There is an equation that we can use to calculate the value of this drag, but we need to know the drag coefficient first. For flow past a ball, determining the drag coefficient gets a little more confusing. The drag on a ball is being generated by the boundary layer separating from the back of the ball. As flow separates, it creates a viscous wake behind the ball. A large, wide wake generates a large amount of drag. A thin wake produces less drag. The thickness of the wake and the drag on the ball depends on the conditions in the boundary layer, which depends on the Reynolds number. At lower Reynolds number's value, the boundary layer is laminar and the wake is thick. As the Reynolds number increases, the boundary layer transitions to turbulent, which initially produces a thinner wake. But with increasing speed and Reynolds number, the wake thickens and the drag increases. Lift. Like the drag, the magnitude of the lift depends on several factors related to the conditions of the air and the object, and the velocity between the object and the air. For a spinning ball, the speed of rotation affects the magnitude of the aerodynamic force, and the direction of the force is perpendicular to the axis of rotation. The orientation of the axis of rotation can be varied by the pitcher when the ball is thrown. If the axis is vertical, the lift force is horizontal and the ball can be made to curve to one side. If the axis is horizontal, the lift force is vertical and the ball can be made to dive or loft depending on the direction of rotation. Let's simplify all this down into an easier to understand simulation. The ball is traveling in this direction means that the air is flowing across it in the opposite direction. But right near the ball there is a thin layer of air dragged around. As oncoming streams of air pass the ball, the side moving in the same direction as the spinning ball is accelerated, follows the curve of the ball, and in this case is deflected off to the right. The side that is moving against the spinning ball meets opposing air and can't continue around the ball. it slows down and continues to go straight. We end up getting a net flow of air to the right, and therefore the ball must move left. Why? Because of Newton's third law. As the air moves in one direction, the ball must move in the other direction. Additionally, since the air is slowing down on the right side, you get a buildup of air, which creates higher pressure on that side and pushes the ball to the left. This is the Magnus effect. So overall, what causes a baseball to curve? Lift, aka the Magnus effect, is what causes the ball to curve. But the ball is also affected by other forces such as weight and drag that affect the trajectory of the ball.